Hello everyone. In this video, I'd like to cover or go over what we took in class regarding the enthalpy changes of reactions occurring in solution. I would like to start by solving an example and introduce a new concept that I would like you to learn and practice using the attached worksheet. First of all, we learned that the enthalpy change of neutralization of a reaction equals negative Q, since neutralization reactions are always exothermic. So it's negative Q, which is the heat released to the solution, divided by the moles of limiting reactants. On the other hand, when calculating the enthalpy changes of solution, which is when we dissolve a solute into a solvent, that is calculated using this equation here, which is the enthalpy change of solution equals the heat released or absorbed by the solution. This is why I have a plus and minus sign, since delta H solution could be either exo or endothermic, divided by the moles of solute that is dissolved in the solvent. We always calculate Q using this equation here, which is heat of solution. It's either the heat released to the solution or heat absorbed by the solution. We always use the mass of water, which we take as the volume of the solution, the total volume of the solution, and we assume that the density of the solution is that of pure water and thus convert it into mass of water. We also use the specific heat capacity of water, and thus there's another assumption here in which we assume the specific heat capacity of the solution is that of pure water, and the temperature rise of the solution. I'll start by solving this example here. Let me make this clear. Okay. So this I've worked out this example and I would like to go over it with you. It states that 50 centimeters cubed of 1 mole per decimeter cubed solution of potassium hydroxide, KOH, were reacted with 50 centimeter cubed of 1 mole per decimeter cubed hydrochloric acid solution. The temperature rise recorded was 6.82. Thus, we know that the enthalpy change of neutralization is always exothermic, and thus a temperature rise, not drop, is recorded. Thus, the enthalpy change would be negative in this case. The first part states or asks to calculate the standard enthalpy change of neutralization for the reaction stated above. I started here, as we discussed in class, by writing the chemical reaction, which is KOH, reacts with hydrochloric acid to form potassium chloride plus H2O. The reaction is a 1-to-1 ratio. We used a volume of 50 centimeters cubed and 1 mole per decimeter cubed concentration for both solutions. Thus, both moles equate to 0.05 moles, which is 1 mole per decimeter cubed concentration multiplied by the volume, 0.05 decimeters cubed. This was converted from centimeter to decimeter cubed for both. And thus, since it's a 1-to-1 reaction, both these moles are limiting, so we're going to use 0.05 moles as our limiting reactant moles when calculating the enthalpy change of neutralization. The next step would be to calculate the heat released to the solution. Q equals mc delta T. The volumes used in this reaction is 50 of sodium hydroxide and 50 of hydrochloric acid. Thus, the total volume of the solution is 100. Assuming it to be pure water and using the density of water, which is 1 gram per centimeter cube, this equates to 100 grams of water. Multiplied by the specific heat capacity of water, which is 4.18 joules per gram Kelvin, multiplied by the temperature rise stated in the question, which was 6.82 degrees Celsius, which is the same as Kelvin, because it's a temperature change. The answer would be 2850.76 joules, and we require it in kilojoules. Thus, I divided it by 1,000 to produce 2.851 kilojoules. So this was the amount of heat released to water by reacting 0.05 moles of limiting reagent. The delta H of neutralization is calculated by dividing Q over the moles of limiting reactant, as seen here. Negative 2.851 kilojoules is divided by 0.05 moles of limiting reagent, which produces negative 57.02 kilojoules per mole. As stated in class, I made it clear that the reaction of a strong acid with a strong base always produces the same enthalpy change of neutralization, which is around negative 57. Thus, if this reaction was repeated over and over again using different strong acids and strong bases, you would produce the same enthalpy change of reaction, of neutralization, sorry. Part B of this question is the new concept I would like to introduce. Part B states the experiment in Part A was repeated using 100 centimeters cubed of 1 mole per decimeter cubed of each solution. In the previous question, we used 50 centimeters cubed of 1 mole per decimeter cubed of each solution. The concentrations were kept constant, but the volumes of both solutions were doubled. And they ask you to calculate the temperature change of the reaction. I'm going to show you the long method of solving this question, which I do not want you to do in a multiple choice exam, and thus I'll show you how to do it in a multiple choice question. But generally speaking, in part A, we calculated the delta H of this reaction as negative 57.02 kilojoules per mole. I converted it to joules here by multiplying it by 1,000, since the specific heat capacity of the solution is in joules. And I plugged in the new volume, which instead of being 50 and 50 of each solution is now 100 and 100 of each solution, which equates to 200 grams of water, assuming its density is that the density of the solution is that of pure water, multiplied by 4.18, multiplied by the unknown temperature rise, and divided by 0.1 moles. The moles have also doubled in this case. Doubling the volume while keeping the concentrations constant has doubled the mass of the solution, as well as doubling the moles of limiting reagent. The moles of the limiting reagent, the new moles of the limiting reagents would be 0.1 decimeter cubed, which is 100 centimeters cubed, multiplied by the same concentration of 1 mole per decimeter cubed, which equates to 0.1 moles. Thus, the new limiting reagent moles when doubling the volumes is 0.1 moles, and the total volume has doubled to 200 centimeters cubed. Thus, both the mass and the moles have doubled, while all other values remain constant. If you calculate delta T, it would produce the same temperature rise as that in the experiment in the previous part of the question, part A, which was 6.82. The concept I need you guys to learn here is that for the same reaction occurring in solution, the volume of the solution as well as the concentration of the solution both will affect the temperature rise measured for the reaction. If you see here, I rewrote this equation. The enthalpy change of a reaction equals mc delta T, which is Q divided by the number of moles, limiting reagent moles N. The specific heat capacity value is always constant, which is 4.18 joules per gram Kelvin, so we can ignore this value, as well as the delta H of the reaction. Since it's the same reaction occurring over and over again, and we're calculating it in kilojoule per mole of reactants, thus this value would remain constant as well. So this value remains constant, and the specific heat capacity value as well would remain constant. Thus, any change in the ratio of mass and moles would affect the temperature rise. But in the previous section, the mass and the moles were both doubled. Thus, the ratio of mass over moles, this is the important part. This is the new concept you need to learn, which is the ratio of the mass over moles. If this ratio does not change, then delta T would remain constant and there would be no change in the temperature rise, as was in the previous example in part B. Since doubling the mass and doubling the amount of moles when doubling the volume of reactants at constant concentration would keep this ratio constant, thus the temperature rise recorded would be the same. Any change in the ratio of mass over moles when compared to a previous example would cause a change in delta T. Thus, for example, if the ratio of mass over moles decreased, this could happen if the moles were increased, if the mass of the solution was increased but the reacting moles were decreased. The ratio here would increase. The ratio of mass over moles would increase. But the temperature rise would be required to decrease to keep the enthalpy change of the solution constant, as stated here. Another possibility would be if if the mass of the solution decreased, but the moles of the limiting reagent increased in the reaction. This would cause the ratio of mass over moles to decrease, and thus to keep the enthalpy change of reaction constant for the same reaction, if the ratio decreases, the temperature rise is required to increase. Thus, in a nutshell, excuse me for a minute, I've summarized these points here. Thus, doubling or halving the volume of reacting solutions while keeping their concentrations constant does not affect the temperature rise, because the ratio of mass of solution heated to the moles of limiting reagent mass over moles remains constant as stated previously. Thus, in a multiple choice question, if you were given a question that gives you the enthalpy change of reaction and gives you and states the temperature rise of reaction, and then they ask you what happens to the temperature rise if the solutions were either doubled in volume or decreased or halved in volume, excuse me, so doubled in volume or halved in volume while keeping their concentrations constant, this never affects the mass to moles ratio, and thus the temperature rise would be the same. On the other hand, if the ratio of mass of solution being heated to moles of limiting reagent changes, then the temperature rise will be affected, as stated previously. If the ratio of mass to moles doubles, then the temperature rise will decrease by half from the previous measured experiment. And if the ratio of mass over moles halves, then the temperature rise will double from the previous measured experiment. The same applies for all enthalpy changes of reaction occurring in solution. One important note that you should also be aware of, excuse me, is in regards to the number of moles and the mass and how they affect the heat released to the solution or the temperature rise of the solution. Thus, in an exothermic or endothermic reaction, the number of moles is responsible for the amount of heat energy taken in or given out by a system. Thus, the greater the number of moles reacting in an exothermic reaction, for example, the greater the amount of heat released to the surroundings, and vice versa. Thus, the moles has a direct effect on the amount of heat energy taken in or given out by a system. On the other hand, the volume of solution being heated, the total volume of solution being heated, will directly affect the measured temperature rise. I give an example here. Consider two different experiments involving the same reaction and the same number of limiting moles. Thus, if the moles are constant, the amount of heat released or absorbed would be constant in both experiments. But in one, 100 centimeter cube total volume of solution is used, while in the other, a total of 150 centimeter cube total volume of solution is used. The higher temperature rise will occur in the solution with the smaller volume of 100 centimeters cubed, since the same amount of heat is released to the solution, but is used to heat a smaller volume of solution. This can be more simply put as using an example of if we get a bucket of water with a large volume and a cup of water, and we give both these solutions the same amount of energy. Let's say both were given 100 or 1,000 kilojoules to heat the solutions. One has a full bucket of water and one has a cup of water. Which one would have the higher temperature rise? Since both were given the same amount of heat, but this heat is used to heat a smaller volume of water in the cup, thus the cup would have a higher temperature rise and the bucket would have a lower temperature rise. I have attached a couple of questions to answer regarding this concept in the attached worksheet. Please attempt to do the worksheet and hand it back as soon as possible, preferably by midnight tonight. Thank you for watching.